In this module, we will continue with our discussion on the valence bond treatment of hydrogen molecule. As we have already discussed in the last module, for the electronic Hamiltonian for hydrogen atom, one can write as it is shown here. You can see here the first two are the kinetic energy terms and the remaining are the potential energy terms. And this electronic Hamiltonian can be written in the form He cap equals Ha1 cap plus Hb2 cap plus H prime cap. Here Ha cap and Hb2 cap are the Hamiltonians of electrons 1 in atom A and electron 2 in atom B respectively, whereas H prime cap is the corresponding potential energy operator. All these terms we have discussed in detail in the earlier module. And we have also seen that the valence bond wave function, which includes only the covalent structures, is given by the form psi Vb equals to psi Ha1 psi Hb2 plus psi Ha2 psi Hb1, and this is written in a general way by the expression C1 psi 1 plus C2 psi 2. So after having done this, now we will be calculating the energy for the hydrogen molecule, and this is given using the variation theorem by the expression Ea equals integral psi valence bond He cap psi valence bond d tau divided by integral psi Vb d tau. Now if we substitute the values of psi Vb as we have done it here, our expression modifies, and if we simplify the above expression, one gets these detailed integrals as you can see here. So we have three terms, or you can see here we have four terms in the numerator and four terms in the denominator, and these are written in detailed form here as you can see here. Now ultimately we have three terms because we have combined the two terms, three terms in the numerator and three terms in the denominator. If we simplify it further, which these integrals can be summarized as you can see here, overlap integral has been defined, and then if we simplify this, on simplification we get the corresponding expression for Ea, which becomes equal to C1 square alpha 1. Here alpha 1 as you can see is the integral psi 1 He cap psi 1 d tau, and alpha 2 is integral psi 2 He cap psi 2 d tau, and then we have beta 1 2 which is psi 1 He cap psi 2 d tau, and that is equal to beta 1 2. Please remember that He cap, which is the electronic Hamiltonian, has three terms which we have already defined, and S is the corresponding overlap integral. So this is the expression which now we get for the approximate energy using valence bond wave function. This expression is Ea equals C1 square alpha 1 plus 2C1 C2 beta 1 2 plus C2 square alpha 2 divided by C1 square plus 2C1 C2 S square plus C2 square. Now we will go into the details of what alpha 1, alpha 2 and beta 1 2 are. Let's look at alpha 1. Alpha 1 is given by the integral psi 1 he cap psi 1 d tau. If we put the detailed expression for psi 1, one gets this. Alpha 1 is equal to integral psi ha1 psi hb2, that is basically what psi 1 was, then he cap psi ha1 psi hb2 d tau. And now if we substitute for electronic Hamiltonian, we get the corresponding expression, which is alpha 1 equals integral psi ha1 psi hb2, then we have ha1 plus hb2 plus h prime cap, then again psi ha1 psi hb2 d tau. If we solve this on further simplification, one notices that substituting some of the integrals which represent the normalization conditions, one notices that ultimately this alpha 1 becomes equal to 2EH, which is 2 times the energy of hydrogen atom plus Q. Q is here integral psi ha1 psi hb2 h prime cap psi ha1 psi hb2 d tau. Similarly, one can derive the expression for alpha 2, and since the two atoms are identical, their atomic orbitals are identical, only the labeling is different. Therefore, one can find out that alpha 2 also will come out to be equal to 2EH plus Q. So after having found out the values of alpha 1 and alpha 2, that means we have found out the expressions for these two. Now let us try to find out how the expression for beta 1 2 simplifies. Beta 1 2, as you can see here, is given by integral psi 1 he cap psi 2 d tau. If we substitute the expressions for psi 1, psi 2 and he cap in this equation, then it gets simplified, and you can notice that if we do it for beta 1 2 or beta 2 1, it will come out to be the same, because it's only a question of labeling. Atoms are identical, and one can notice that therefore one can define beta in general instead of beta 1 2 or beta 2 1, and this beta becomes equal to, as you can see here, equals to 2EH s square plus A. S is the overlap integral, which we have already studied earlier, and A is an integral which is equal to integral psi ha1 psi hb2 h prime cap psi ha2 psi hb1 d tau. Therefore, once we have got the expressions for alpha and betas, we can find out that our total energy EA, which we had calculated, that expression, which was our C1 square alpha 1 plus 2 C1 C2 beta 1 2 plus C2 square alpha 2 divided by C1 square plus 2 C1 C2 S square plus C2. Now one can further solve this, and if we rearrange this equation, as you will see we have done it here, and then differentiate with respect to the coefficients, one ultimately gets the corresponding secular equations, which can be written in the form. On the left hand side we have this alpha 1 minus EA, then beta 1 2 minus EA s square upon beta 1 2 minus EA s square upon alpha 2 minus EA, then we have C1 and C2. If one simplifies this, these secular equations will have non-trivial solution only if the determinant, secular determinant, is equal to 0. And since we have already defined alpha 1 and alpha 2 equal to alpha, and beta 1 2 and beta 2 1 are equal and they are equal to beta. Therefore, with these consideration, the ultimate solution one gets is that EA has two values. One is EA plus, which is alpha plus beta upon 1 plus s square. And the second is EA minus, which is alpha minus beta upon 1 minus s square. This is ultimately, we are getting through the use of variation theorem and using the approximate wave function constructed using valence bond treatment. Now in these two equations, if we substitute the values of alpha and beta in this energy expressions, we will get EA plus to be equal to 2EH plus Q, that was basically the expression for alpha, plus 2EH s square plus A, that was the expression for beta, divided by 1 plus s square, and this further simplifies to 2EH plus Q plus A upon 1 plus s square, as you can see it here. And then we also have another expression for EA negative, which can be similarly obtained, and this comes out to be equal to 2EH plus Q minus A upon 1 minus s squares. We have still to find out the details of Q and A because we have already defined them. But what are these basically Q and A? These things we will be ultimately studying in the next module. And we will also take up the expressions for the coefficients C1 and C2 in our next module, along with the discussion of the potential energy curve for hydrogen molecule. So you have seen that in this module, which basically details the valence bond treatment of hydrogen molecule, we use the valence bond wave function, which was psi Vb is equal to psi Ha1 psi Hb2 plus psi Ha2 psi Hb1, and that we took in the general form C1 psi 1 plus C2 psi 2, where we need to find out the values of the coefficient C1 and C2. Here, as you remember, psi Ha and psi Hb represent 1s atomic orbitals for the two hydrogen atoms. And in one, as you can see, electron 1 is around atom A, and in the second, electron 1 is on atom 2, that means atom A, whereas electron 2 is on atom B, and in the second, electron 1 is on nucleus B. So that's basically how we constructed the valence bond wave function. Then we calculated the energy for the hydrogen atom using the variation principle. This was the expression which we used, and this expression on simplification gave us the corresponding energy EA, which was equal to C1 square alpha 1 plus 2 C1 C2 beta 1 2 plus C2 square alpha 2 divided by C1 square plus 2 C1 C2 S square plus C2 square. Here we had defined what are the integrals alpha 1, alpha 2 and beta 1, 2. As you can see, they are very easy to remember. In all of them, there is electronic Hamiltonian which is coming. In alpha 1, it is psi 1 and psi 1, both are coming. Whereas in alpha 2, psi 2 is coming. Whereas in beta 1, 2, it is both beta 1, psi 1 and psi 2 which are coming. We have simplified these integrals and found out that the values of alpha 1 and alpha 2 come out to be the same because the two atoms are identical and they are equal to 2EH plus Q. whereas the values of the beta 1, 2 comes out to be 2EH S square plus A. By solving this secular determinant, we got the two energy expressions. One was EA plus and second was EA minus. As you remember, we found out that EA plus has its expression which is given by 2EAH plus Q plus A upon 1 plus S square, whereas EA negative has its value equal to 2EH plus Q minus A upon 1 minus S square. In the next module, we will go one step ahead, find out the values of the coefficients and study some other details about the hydrogen molecule.